All right, it's 4 o'clock. Let's go ahead and start the course. Okay, so first thing is I have a couple of announcements. The first announcement has to do with your homework assignment. Your homework assignment has been uploaded, the final homework assignment. So once this thing comes back up. So homework number 6 is going to be due. How come you can't scroll here? Okay. Homework number 6 is going to be due on May 1st, which is the last day of class. Our final is on the Friday. This is due on the Wednesday, all right? There are only 4 problems. The first problem is to read the course notes, so you get free 10 points there. We have to read, right? And then the second problem is Keller's GTD paper. You're going to read the paper. I uploaded it to Canvas. It's a very good paper, fundamental paper on the theory of geometrical theory of diffraction from Keller. And you're just going to write an English summary of the paper. So you don't have to derive the equations or you don't have to produce any quantitative analysis. Just provide an English summary of the paper, right? What is the paper about? You know, maybe each section of the paper. Say this section discuss this section discuss that, right? All right. Okay, the third problem is going to be a tough one, but I've written all the code for you guys. So you just have to adapt the code, all right? And this is the reason I'm bringing this up now is because today's lecture, we're going to go over this program that I wrote over the weekend to give you guys some example on geometrical optics. So you're going to be able to take that program and adapt it to this particular problem. So the problem says what you're going to be doing is taking a point source at this location here, the focal point, and this is a dual reflector system called a Cassegrain dual reflector system. This is a hyperboloid, and this is a paraboloid. And they are confocal, meaning that the hyperboloid has how many foci? 2, right? So these 2 x's here are the foci of the hyperboloid. All right? So, and then the main reflector is a paraboloid. How many foci does it have? 1, right? So confocal means that you align the foci of these 2 systems. So the secondary reflector is this hyperboloid, and it's referred to as S, right? DS and FS, right? So DS is the diameter of the secondary reflector, and FS is the focal length of the secondary reflector. See how it's the distance between the 2 foci here, all right? The paraboloid has its foci. Where do you think the paraboloid's foci is? Have you guys taken a class in antennas? Okay, so you want to align the foci of these 2 reflectors, and here you have the 2 foci of the hyperboloid, right? Okay. The feed goes at one of the foci, and the other foci is called, or the other focus is called the virtual focus, if you will. You take the paraboloid, what? Oh. You take the paraboloid, and you place its focus at the virtual focus of the hyperboloid, right? So what happens? If you put the feed at this foci, it radiates, it scatters off of the hyperboloid, and it makes its way to the main reflector, the paraboloid. But because of the way these foci work, it's as if you are imaging this feed to the other focus, right? So what you could think about is removing this hyperboloid and placing the feed at the virtual focus, and that illuminates the main. It's the same thing, right? Does it make sense? All right, anyway, it's just the geometry of a dual reflector system. So you're going to have a point source at this place where you place the feed. It's going to illuminate. You're going to represent that point source as rays, and you're going to have a spherical wave front, right? It's a point source. It's going to illuminate the subreflector. You're going to calculate the scattering, the reflection of the point source as rays from the subreflector, and then you're going to parameterize the paraboloid as an aperture where you're going to collect 2n cross hi. All right, that's it. All right, and this is a very useful thing to do as a homework, right? All the parameters are here. If there's something that you guys run into that we need to add to this problem for it being not clear, then let me know. but the primary reflector's diameter is dp. The primary reflector's focus is fp. This table gives you all the parameters in this figure. F over d is 0.5, so the diameter is twice the focal length for the primary. The focal length of the secondary reflector, the distance between its two foci, is 450 millimeter, and the diameter of the secondary reflector is 240 millimeter. All right? This SF is 0, meaning you put the feed phase center at the focus of the hyperboloid, and this SS defines the distance from the tip of the secondary reflector to its virtual foci, but don't worry about that, all right? Okay. So you should have all the parameters you need to parameterize this thing, and you will trace rays from the phase center of the feed, which is a point source, and I'll show you how to do all that, right? From here to the hyperboloid, reflect from the hyperboloid, and follow the ray to the paraboloid's parameterization. You know this is PEC, so that means that there's no magnetic current here, and because E tangential is 0, so you just find the magnetic field along this paraboloidal surface, and you calculate 2n cross hi. And it's very easy to calculate h once you have E using geometrical optics, all right? Okay, is it clear? It will be when you start to...
Rays are going to came out bottle.
No. This is a point source here. The point source goes at one of the foci. I wish I could draw on this thing, but so here's a hyperboloid. It has two foci, these two x's, right? And here's a paraboloid who has one foci. We place the foci of the paraboloid to coincide confocal with this focus of the hyperboloid, all right? Now, that means that because this is the focus of the paraboloid, if I were to put a feed here, then it would generate a plane wave or uniform phase in the aperture, right? But instead of doing that, we fold the optics, is what they call it, where you compress the system by placing a feed at the other focus of the subreflector. And then because both of these are foci of the subreflector, placing a feed here is exactly the same as placing a feed here by nature of the way that the optics work on these conic sections. So now this foci, I put a point source there. It radiates to the subreflector, reflects off the subreflector. As soon as it reflects off the subreflector, it looks exactly like it was emanating from this foci behind the subreflector by nature of the way the optics work. So it'll radiate here, reflect, and it'll go to the main, and then you'll calculate the induced surface current on the main. And then you can integrate that using physical optics if you want. So at the end of this, you're going to write a program which is pretty useful.
It's going to be a plane wave.
It's not a plane wave, right? There's a point source here at this foci. So a point source is a spherical wave, right? So it's going to be a spherical wave which radiates this way. You only calculate the rays which intercept the hyperboloid. Of course, a point source there is a bad model. You want to put some taper to it so you don't have a bunch of spillover, but we're not worried about that right now, right? So trace rays from here to here. Incident field is a cylindrical wave, reflects off of the hyperboloid and goes to the main. And by the way that the nature of these optics are set up, it looks exactly like a point source which is imaged to the other foci emanating from here without the sub by nature of the reflection, yeah? Okay, good. So it sounds like a crazy problem right now, but it's not that difficult because we're going to go over the code that I already wrote for you. You just have to adapt it. Okay, so number 4 is the derivation of the radii of curvature of the diffracted wavefront and the geometrical theory of diffraction solution for the diffracted field. And you're going to detail the steps needed to do that, which means go through the notes, understand them, write them out. You'll probably want to wait till after next lecture to do this one, but start this one as soon as possible, number 3, and read the GTD paper too. All right? So you have 10 days to do this homework. And that'll be the last homework for the class. If we have time, we're going to get to UTD and UAT, which are the uniform asymptotic theories and uniform theory of diffraction, which solves one of the problems of the shortcomings of the geometrical theory of diffraction. and we'll see if we have time for that, right? But you won't be able to have a homework on it, so it'll just be something you can follow up on with your own interests. All right? Okay, don't wait for this homework either. All right. So, in order for us to understand the geometrical optics program, I'm going to review quickly the formulas that we need to derive, to write the program, all right? So, as a quick overview, we started with the asymptotic solution to Maxwell's equations, right? We expanded the electric field in terms of the Lunenburg-Klein expansion, right? Which is an asymptotic series in terms of inverse powers of K. And there was this parameter tau, which we said was 0 for geometrical optics, and that's how we've seen it. But now, today, we're going to introduce the -1/2 coefficient or exponent for K when we do the geometrical theory of diffraction, when we study diffraction. All right? Okay. So we plugged that expansion in Maxwell's equations and turned the crank, and we found the Eichel equation and the transport equation. The Eichel equation is here, and it tells you the shape of the rays. When we solved this, we found the rays are straight lines, right? That's the solution to this differential equation. It's a differential equation. There are derivatives in this Nabla operator, right? Or the del operator. And therefore, this is a differential equation. The solution to that differential equation we found was a straight line parameterization. Because the rays are straight, we now know that, and it also tells you the shape of the wavefronts, right? The wavefronts, so what is S? S is the phase function, right? With respect to some point, let's say here, we have this function S of R. So from here, we can say this is S of R, right? S of R1. Let's say this point is R1. This point is R1, right? Or this point, this is S of R2, right? And this point is R2. So there'd be another, let me see, another vector here, which is R1. This vector to this point is R2, right? Okay, now, the point to this S function is for S of R being a constant, so S of R equals to a constant. So that means let's take this as the constant we're going to use. All other R which satisfy S of R as a constant define an equa-S contour or an equa-S surface, right? That equa-S surface is an equiphase surface because S is used for the phase, right? It's here. So it's an equiphase surface. Equiphase surface, and therefore the phase is constant along this whole surface. Therefore, it's a wavefront, right? It's a wavefront. All right, so the gradient to a equisurface is in what direction?
Normal.
Normal, right? So that means this is the gradient of S. This is the gradient, oh my goodness. This is the gradient of S, right? So gradient of S are the rays. All right, and S are the equiphase surfaces. All right, very good. So that was the Eichel equation. It told us the relationship between the rays and the surfaces, the equiphase surfaces, the wavefronts, the rays and the wavefronts. Then there was the transport equation, which was a differential equation that we derived, that we also solved, which told us how to calculate the variation of the amplitude along the ray, right, of the electric field. We're only concerned with the zeroth order solution or the leading term of the Lunenburg-Klein expansion in this course. So it told us how the amplitude changes along the ray. And what did that turn out to be? When we solved the Eichel equation, what did we find? You guys remember? So we solved the Eichel equation, and we found as its solution this expression here. That was the solution to that differential equation, the transport equation. And what it means is the electric field at point B, for example. Okay, so here, the electric point at the magnitude of the electric field at point sigma along a ray. So here's a point R naught. Here's a point R. The electric field at point R with respect to its value at R naught was given by this factor called the divergence factor multiplied by the electric field at point R naught, right? Yeah? So the electric field can be continued along a ray, the whole electric field now. We're going to use this expression in our code today. The electric field can be continued along a ray given the electric field at some initial point on the ray or reference point multiplied by the divergence factor and the change in phase. So it looks locally like a plane wave, right? Although it's not a plane wave, what would be different about this if it were a plane wave, a pure plane wave? What? Very good. Right? The electric field on a plane wave does not change amplitude. If it's a spherical wave or it has any curvature to the wavefront, then it will decay, right? Because the electric field is decreasing so that the power density remains constant with respect to a lossless medium. All right? And sigma minus sigma naught is nothing but the integrated arc length along the ray, which is, in the case of straight lines, the distance formula between the 2 points that you're considering, right? Okay, good. So we're going to need all of that. So now we calculate the geometrical optics solution. We have two fields to consider now. The incident field, which has its Lunenburg-Klein asymptotic expansion, and the reflected field, which has a different uniform or Lunenburg-Klein asymptotic expansion, right? Okay. And we add these two together, incident plus reflected, right? If you want to know the total field at some point, it's the incident plus the reflected. If the incident field goes to that point, right? Okay. And there's these shadow indicators to indicate that the geometrical optics solution does not, it gives a zero field in any shadow region. All right. Okay. So all of the next things that we did was how to calculate the reflected Q matrix, which has our radii of curvature of the reflected wavefront in it, which allows us to calculate the divergence factor so that we can continue the ray from the reflection point to the next point of interest. All right. Okay. So how we did that was we came up with three constructs. The first is the incident pencil. We can't just consider a single axial ray. Why is that? What differentiates this from the optics you learned in high school?
The paraxial rays.
Why do we need the paraxial rays? Remember, the paraxial rays, the amplitude is related to the differential surface area, the change in the differential surface area enclosed by a flux tube of rays, right? So we can't just use the axial ray to find the amplitudes. In high school optics, you just followed rays and calculated their length, and therefore things were only dependent on phase. But we couldn't calculate the amplitudes, right? In this theory, you need a group of paraxial rays which surround the axial ray, therefore forming a flux tube of rays or a pencil of rays in order to calculate the cross-sectional area of that flux tube and to see how it changes. So you can calculate the amplitude, right? So when we're calculating the reflected Q matrix, which is related to the curvature matrix of the reflected wavefront, we needed neighboring rays. We needed the whole tube, right? So we defined three pencils, or three constructs. First, the incident pencil, then the reflected pencil, then the screen sigma. Okay? Okay, but we needed coordinate systems in order to perform this boundary condition. This is what really mattered. N cross E incident plus E scattered or E reflected equal to 0 on the screen sigma, on the reflecting surface, right? In order to apply that boundary condition, PEC tangential E goes to 0, we needed to match the phase of the incident reflected fields, right? It's called phase matching. And in order to do that, for R on sigma, we needed to do it over a region on the surface. So the incident pencil, the axial ray is there, but we need to also match the phase fronts over a neighborhood of the axial ray on the surface, which means we need to describe the incident pencil at all of these points so we can calculate S incident, which means you need to express the incident pencil's phase function in the local surface coordinate system and the reflected pencil similarly. And that's what we did last time, right? At the end of all of that, so the pencil coordinates, we're going to need those today too, right? So the pencil coordinates, let's see. The pencil coordinates have X, oh man, why does it do that? X1 incident, X2 incident, and Z incident. Z incident is always along the axial ray, and then X1 incident and X2 incident hopefully are in the principal directions of the incident wavefront. If they are, what happens to the Q matrix? If we're in the principal coordinate system, it's diagonal because the principal directions are the eigenbasis of the curvature matrix. Okay? This coordinate system, breaking the vector into this coordinate system is not necessary for us because we're not calculating higher order amplitudes. All right? We're not doing amplitude matching. But anyway, it's there. Okay. So the incident SI that we need for phase matching to satisfy the boundary condition of tangential E goes to 0 on the curved surface of the screen is given by this. Do you remember what this is? The incident reference, the phase of the reference points, plus the axial distance along the axial ray, plus the second order quadratic approximation of the wavefront at the observation point Zi along the ray, which means you need to propagate the Q matrix to the new point, all right? We define a reflected pencil in the same way. All of those pencils need to be described in the surface coordinates. The surface coordinates are x1 sigma, x2 sigma, z sigma. But what matters is not just that point. That's the axial ray incidence and reflection point, right? The point O is the point of reflection. What matters is neighboring points as well. So we need this n. This is the n that goes in the boundary condition, n crossed with E incident plus E scattered equal to 0. So there's another coordinate system here, sigma 1, sigma 2, and n, which has its components described in terms of this main coordinate system here. All right? Everything's going to be in these components. We're going to describe the components of these vectors in terms of those. All right? Anyway, you do all of that, and you get the following expression, which we derived, right? Here's the phase matching. So here's S incident in the surface coordinates, right? These are all surface coordinates now. And what have we found? What do we find by doing this? S incident, the incident pencil's phase function, is expressed not only in terms of the incident Q matrix, but it's affected or picks up the curvature of the surface, right? Because we're talking about what is the phase of the incident pencil at this point, right? Well, the incident pencil might have a wavefront like this, and therefore, and the tangent coordinates like that, right? So let's say like that, and z. So there's this distance, epsilon, which is the second order quadratic approximation defined above the tangent plane of the incident wavefront, plus the surface itself has some curvature there. So you have to add that epsilon with respect to the wavefront surface described in the local coordinate system. So you have two curvatures, right? The incident wavefront has some curvature. The surface has curvature. You have to consider both of those to find the actual phase or the length of the axial ray or paraxial ray to some point on the surface, right? All right. So you have to see the derivation, but at the end, you're going to see the program is a lot more simple than you think. You don't have to think about all these coordinate systems and things. We just need to use the result we derived, right? Which is this. So here's S incident. Here's S reflected the same way. And now we can do phase matching. And what we find when we do phase matching is this expression here, right? This equality. What we're going to do now is match. We have to satisfy that equality. So constant terms equal to each other, linear terms equal to each other, quadratic terms equal to each other. So here's the linear terms, we get the Snell's law of reflection. That's useful. And matching the quadratic terms, we get a way to calculate the reflected Q matrix. We'll use this today in our program, okay? So Q reflected at the point of reflection, where Z reflected is equal to 0, right? Is equal to Q incident. The curvature matrix of the incident field propagates itself to the reflected Q matrix curvature, plus the projection matrices of the coordinate systems, right? To describe the incident pencil and the reflected pencil in the surface coordinates, we had to do a bunch of projections of the vectors of the incident pencil onto the vectors of the the surface coordinate system. So we had to do all that, right? Anyway, and the curvature matrix of the surface locally affects the curvature matrix of the reflected wavefront, right? And the incident curvature matrix. Makes sense, yeah? All right. Once we have, so the way we were able to calculate this was we got rid of the reflected Q, all of this reflected and P2D reflected, we related it back to P2D incident and P incident. So we can cancel all of that, right? And the way we did that is we reflected the incident principal directions, the incident pencil coordinate transverse vectors off of the surface to get the reflected pencil coordinates tangential basis vectors, yeah? Okay, but that gives us a left-handed coordinate system and all of that, but we can fix that later. So what that did was say that PI is equal to PR. Great. Now, because of that, we're able to derive this, and it's not a function of PR. We don't know PR, right? We do because we define it arbitrarily to be this. Because we defined it arbitrarily, the reflected pencil base vectors in the tangent plane of the reflected wavefront may not be aligned with the principal directions of the reflected wavefront. But since we have the reflected Q matrix, the reflected wavefront's Q matrix, we can easily calculate what those principal directions are, and then we can rotate into that coordinate system. All right? Okay, we're going to do all this in this program that we're going to go over right now that I spent the weekend writing and debugging. All right. Okay, let's get into that. So here's the program. So consider the calculation of the field of an x-hat directed point source. So here's the geometry. Let's see. The geometry is like this, right? We have some sphere here. It's a PEC sphere. There's a PEC sphere. And that sphere is centered at the origin of this coordinate system, right? And the feed here, there's a point source here. But of course, the point source is not a solution to Maxwell's equation. So it has to be an x-hat polarized point source, right? The x-hat polarized point source, let me write down the function for that, is E, say incident, is equal to E to the minus j k r over r. And then we have theta hat cosine of phi minus phi hat sine of phi. All right? So what does this mean? So e to the minus j k r over r, that's a spherical wave, right? So that's just a point source. But then we have this thing, which is the polarization, right? It's a unit vector in the direction of the polarization of the electric field. Now, when, so let's draw an x, y, z here. So here's x, y, and z, right? Now, when phi is equal to 0, what plane am I in?
The XC.
Very good, xz, right? So that means there's no phi component of this field, E incident, in the xz plane. There's only theta, right? So let's say, talking about this point here, theta is there, right? Yeah? So is that mostly along x or along y? It has both an x and a z component, right? But who cares about the z for now? We want this point source to be dominantly x polarized. So it has a component in the x direction, nothing in the y, right? Very good. Now, let's observe what happens in the phi equal to 90. What plane am I in then?
YC.
YZ. Now, what's the polarization of phi equal to 90?
X.
Minus phi hat, right? From this term. So that means phi hat normally points in what direction when you're in the YZ plane? Phi hat.
X.
Phi hat points. So remember, phi, first off, phi points, when phi is equal to 0, points this way, right? Orthogonal to the x-axis. Now imagine sweeping this around 90 degrees. What direction is it going to point? Minus x hat, right? That's why you need this other minus sign. So once you get to the YZ plane, it's still x polarized. All right? Okay, so you put that kind of source here at a distance b, away from the sphere of radius a. All right, so we have some ray we're going to launch here. That ray is going to carry a piece of a wavefront associated with it, right? That wavefront has a pencil coordinate system, x1, x2, and z incident, right? x1 incident, x2 incident, z incident. Because this, okay, so from that feed, right? E to the minus j k r. Oh, by the way, I wrote the program in e to the j omega t. And your notes are in e to the minus I omega t. Nothing changes except for the minus. This is the only thing that changes, all right? All right. E to the minus j k r over r, theta hat cosine of phi minus phi hat sine of phi. All right. What kind of phase front is this? What is the shape of the phase front? It's a sphere, right? It's spherical. This is it, e to the minus jkr. This is just the direction of the electric field. The phase front is e to the minus jkr, right? So that phase front is a sphere. That means that what do you call? Okay, so what are the principal directions of that phase front?
So they are equal, right?
What are equal?
Because the radius of curvature is the same in both sides and spheres.
Very good. So what is that point called? I don't know if you remember. It's called an umbilic point, which means if the curvature is the same in all directions, it's an umbilic point, which means any directions are the principal directions, right? So you can choose the principal directions anywhere you want, right, for the incident wavefront. All right. Now, that's going to meet the sphere at some point, and it's going to reflect from the sphere according to Snell's law. Theta incident equal to theta reflected, right? All right. Then we're going to calculate the reflected wavefront. It has its own coordinate system, and we're going to follow that reflected wavefront until it meets an aperture here, which is spherical. So the reflecting surface is spherical. The incident wavefront is spherical. The aperture where we're collecting the wavefront, or the reflected field, is spherical. All right? The reflected wavefront, is it always spherical or not? No. Very good. Very good. Okay. Especially when we come in oblique. If we start here and we go to some point which is in a different plane, it's going to see a different, it's going to see the projected sphere, right? Start looking ellipsoidal. All right. So here's some plots that I made with the code. So what you're going to see, this is a two-dimensional cross section. I trace rays one at a time. They reflect off of this. I calculate the reflected ray, right? Same with this. You can see here I do a sweep in phi at a new theta. I sweep in phi again at a new theta. So I launch rays at a particular angle. Then I sweep all the phi, and we can calculate what the reflected ray is. And you can draw these ray plots. All right? Okay. So what happened here? What goes here? What is that? Shadow boundary, very good. So you could probably get one more ray here that goes like that. But then what happens back here? Shadow, right? Nothing. Very good. All right. Okay, so here's the run of the program. I collected the aperture field, E aperture theta, and E aperture phi. And we got the magnitude and phase of that electric field as a function of theta. So what is this theta and what is this phi? Whoops. What is this phi here? It's plotted as a theta phi. Those are the coordinates of the points of the reflected field at, this is a theta. Oh no, theta is here. Sorry, let me clean this up. So from here to there, this is theta, and phi is the angle to here, right? So it's the theta phi of the position vector to the point in the aperture sphere that I'm plotting the electric field at. All right, is it clear? Because the electric field here, there's a position vector which describes that point, r, right? And that r is the result of the parameterization of array. Call this b, for example, and this a. Then the parameterization of that array is b plus t into a. Well, that's equal to this r right here, right? Okay, all right. Anyway, so here, so and then I ran it with FACO, right? And here's the FACO model. You can't see it, but this thing. So what did I run it for? I should have put that here. This is a 5 lambda. All right, so let me show you what. So the radius of this is 5 lambda, right? The point source here is located at 7 lambda. Let me clean that up. 7 lambda. And the aperture plane is at 7.5 lambda at 10 gigahertz. All right. All right. So this sphere, you can't see it, but if you were to zoom in closely here, it has got a ton of surface triangles on it. All right. This thing is all tessellated with triangles because it's a 10 lambda sphere, right? The point source is right there. And you can import the exact same point source into FACO, illuminate the sphere, and calculate the scattered field from that sphere. And it takes hours on a multi-core system in parallel. All right? Geo takes seconds. It's fast, right? It's much, you don't have to do any coupling. You don't have to solve a matrix equation. You launch array, you parameterize it, you find the point of reflection, and then you go to the aperture and you store the electric field there. It's super fast, all right? So you can optimize things. All right, so these scales are a little different, right? Like, for example, here, 3 is like a lime green, but here, 3 is almost green, you know, but it has some yellow in it. It's not exactly the same scale. I had to do this quickly, so, but I tried to get the scales to line up. So you got to be cognizant of that, right? What you could do is look here. So here at like 150, for example, we have like a yellowish green, and a yellowish green here is like maybe 4. And here at 150, we have this point, which is about 4 is almost red, right? So it's hard. It does. They are in agreement. Is what I'm trying to get at. The scales are a little different. So here's E theta. It has 3 lobes. So do we have 3 lobes here? Here's E phi, 2 lobes, and then the phase matches up, right? All right, cool. So let's go to the program now. So you're going to need this code for your homework. What do we do first? We clear all, close all. Then we define the parameters. 10 gigahertz is the frequency. Then we calculate lambda and k from that. You define the radius of the sphere, which is 5 lambda a. B is the distance to the point source. C is the radius to the aperture. And then there's this flag here to make a 2D plot or 3D plot of the rays. All right, first we parameterize the geometry. The surface with the S is a sphere. Here's the parameterization of a sphere. For your homework, you're going to change this to hyperboloid, right? All right. But this is a sphere. And A sine U cosine V and so forth, right? Then, oh my God, it always does that. Okay, 1 second. One second, sorry. Because it always changes my font. So I need to go here and produce the size of this. How do I do that? Gosh, sorry guys. Let me see if I can. I don't know how to change the. Oh, here we go. Good. All right. Just give me 1 second here. Is it this one? No. This one. Yeah, that one. Okay. I gotta do that for all of these. Just give me a second here. That one. Okay, that one's fine. This one. This one as well. So it worked fine in my slides, but when I used the PowerPoint for the iPad, it always changes the way it displays. I don't know why. Okay. And here, this will be the last one. Okay, good. Now. Okay. All right. So, all right, we're back. Yeah. Okay. So here. All right. So parameterize the sphere. A sine U cosine V, A sine U sine V, and A cosine U, right? Now we need all the derivatives so that we can calculate, the first and second fundamental forms, right? So the derivatives here, RU, and then we calculate RV, and then we calculate RUU, RVV, UV, and RVU. Those are all for the X components, right? Same thing for the Y and the Z components here, all right? Okay, then we need the parameterization for the ray. The way we've set this up is they're functions, right? So these are functions of U and V, and this is a function of T, but I also added the direction of the ray. Because the tangent vector, so let's go back here, because of the point source is located along the z-axis and has its coordinate system in the same orientation as the global coordinate system, then this ray, which is emanating from there with these angles theta phi, is the same as the theta phi in the global coordinate system. So you don't need multiple coordinate systems. You can do everything in the global, right? Anyway, the tangent vector that you need to parameterize this ray is a function of theta and phi, right? It's a unit vector r. So that's why I added this theta and phi here for the launch angles of the rays. All right? Okay. So there's an x, y, z. Now, let's begin the ray plot. So this is nothing but initializing the ray plot. So we have figure, hold, grid, axis equal. Don't worry about the GCA or the reversal of the x-axis. So plot 2D is here. So in a 2D plot, you basically draw a circle here first, right? With the, you draw a circle and then you set the axes and all this. There's no rays yet. I'm just setting up the plot, all right? With the circle and the point source. So here's the point source. And here's the 3D. Whoops, gosh. The 3D here, you can call this function sphere. It gives you the XYZ coordinates of a sphere, and then you just draw it using the surf command. And then you add the point source here, right? But now it's scatter 3 because it's 3D plot. All right. Now we loop over the launched rays. So we need to define the launch ray angles. So here's a vector of theta and a vector of phi for the rays. We're going from 1 to 42 degrees. In theta, 21 rays. Why did I stop at 42 degrees? That's right. The rest of the rays are, they don't intersect the sphere, right? And then phi, we go from 0 to 2 pi and 181. So every 2 degrees. And then, okay, so this I had to do for whatever. Okay, so here, what do? First, we loop over theta and phi. So we loop over all the rays, right? We're going to loop over all the launched rays. And we're going to calculate. So here's how you solve for the intersection point of a ray and a surface. You define, the way I did it was these 3 symbolic variables, T, U, and V. That's what we're solving for, right? And in that T, U, and V, we use VPA solve, which means variable precision arithmetic solve. It's a numerical solve using Gauss, or not Gauss, Newton-Raphson gradient descent type of thing. Or maybe not, it's not gradient descent. It's Newton-Raphson root finding, basically, right?
Is it a MATLAB function?
It's a MATLAB function, yeah, VPA solve. And what you send to that is the vector. So here's a bracket, and here's another bracket. There are 3 equations in this bracket. X of the ray is equal to X of the surface. and y of the ray is equal to y of the surface. Z of the ray is equal to z of the surface. This is a function of t, u, and v, right? Here are the three variables. The next thing you tell it is what are the three variables you're solving for. And the next thing is the initial conditions. You need good initial conditions for this variable precision arithmetic solver, all right? Okay, so what is this saying? This is saying that there is a point which has x, y, and z coordinates. There is a point where the position vector of the ray is equal to the position vector of the surface, right? The ray and the surface intersect at one point in space that has x, y, z coordinates where the two parameterizations predict the same spot, the same x, y, z coordinates. So you're solving for the parameters of those parameterizations, and the return of that function is the t, u, and v where that intersection happens. All right? All right. So once you have that, you need to check if it's empty, right? If t, u, v if it doesn't intersect, if there's no solution, then it'll return empty. So if it returns empty, you skip the ray. If it returns empty, you display ray did not intersect sphere, and you fill these are matrices holding the aperture fields and the intersection point in the aperture field. You fill them with nands. That's what I did, because then you can easily go and remove them later. All right. If it did intersect, then none of those three, all three of them would not be empty. And okay, this returns the symbolic t, u, and v. You need to convert it to a double data type number. All right, so you just say double t, double u, double v, yeah? Okay, so now we've computed the intersection point. So now we launched array from the feed and we found the intersection point. So we know the t, the parameter of the ray, how long it is then, right? It's t long, right? Because it started at 0. And it has length t, all right? And we know the UV parameters of the surface parameterization of the intersection point. Now what we need to do, so basically we've done this, right? So here's here's x. We know this t now, the length of this thing is t, right? And we know this vector r of u and v, and this one is r of t, right? So we know t now, yeah? All right, so now we have this point here. We need to find the local coordinate system of the surface at that point. So how do we do that? Well, we first we calculate rs, because we know u and v now, right? So these aren't variables anymore. We're passing in known values, so we're evaluating the parameterization at that point, the intersection point. So we calculate rs. This is rs, right? Then we calculate all its derivatives, and the normal, RSU cross RSV. RSU is the first tangent vector, and RSV is the second tangent vector, right? RU is a tangent vector, RV is a tangent vector. Okay. Now, you can take the cross product of those, you get the normal. First fundamental form, big E, big F, and big G is the dot product of RSU, RU, and RV, R, okay, gosh. Sound like a seal or something. Oh. Okay, RU is RSU, or RU dotted with RU, is capital E. Capital F is RSU dotted with RSV. And capital G is RSV dotted with RSV, yeah? Okay, now, then we calculate little e, little f, and little g as the dot product of RSUU with n, and RUV dotted with n, and RVV dotted with n, all right? Yeah? Okay, once we have the first and second fundamental form parameters, then we can calculate Q matrices next. Q11, Q12, Q21, Q22 in terms of those first and second fundamental form parameters. Once we have that, we can form the Q matrix of the surface, QS. Then we can use the eigen function in MATLAB to calculate the eigenvalues and eigenvectors of that Q matrix, right? And what do we get? We get this vector D. Remember, we did this before. Then you multiply the inverse of D by RSU and RSV to get XS1, XS2, which are the principal directions of the sphere, right? What do we expect XS1 and XS2 to be? First off, what do we expect the eigenvalues, which are? What are the eigenvalues of the Q matrix? Very nice. 1 over A, right? And it's a diagonal matrix. So XS1 and XS2, they're any direction, right? The sphere is umbilic at every point. All right. So now we have XS1, XS2, we have the normal to the surface, and we have the Q matrix to the surface. All right, we need all those. All right, now we compute the incident field at the intersection point, which means we need S, which is the phase function along the axial ray from the feed to the sphere, right? We calculated the length of that already, it's T, right? Which is the parameter, because T equal to 0 puts you at the feed, right? And T equals to the T that we solve for the intersection point puts you on the sphere. So the length of that ray is T. All right. The incident field is spherical, so it has radii of curvature 1 over T, which is the distance from the feed phase center to the intersection point on the sphere, and it's diagonal because it's spherical. E incident here is nothing but okay, so there's X. This is a matrix with 3 components, right? There's an X hat component, a Y hat component, and a Z hat component. And we've taken theta hat and phi hat from that vector, which was cosine of phi theta hat minus sine of phi hat. And we've converted this into X hat, Y hat, and Z hat components. That's all that this is, right? So you'll see cosine theta, cosine phi is the conversion from theta to X, and then we have cosine phi. And then sine phi minus sine phi is the conversion of phi hat to X, and then there's also sine phi here from the feed function, right? You can go through this and see it. Now, divergence factor, we didn't calculate. The divergence factor is nothing but the square root of, okay, so the formula for the divergence factor in terms of the Q matrix was square root of the determinant of Q at sigma divided by the determinant of Q at sigma naught, right? But sigma naught is the initial point, so we don't need that. So in this point, for this particular case, the incident field is just a determinant of Q incident, right? All right. So multiply by the divergence factor, E incident, multiply by the divergence factor, multiply by E to the minus JKS. And I use minus J here instead of plus I. And S is nothing but the length of the ray from the feed phase center to the sphere, yeah? Okay. Now, we have Ri, which is a vector, the position vector to the from the global coordinate origin to the intersection point. Wait, let me say that again. No, this should be called yeah, so Ri is the vector from here to here. This whole thing is Ri, R incident. All right? So the unit vector is our Zi of our incident pencil. The axial ray Ri, right? All right. Now we can calculate xi1 and xi2 as any 2 vectors because the incident field is a spherical wave. So we just pick Ri crossed with Z hat. All right, so we have X, Y, and Z. We have some Ri, for example. Take the cross product of Ri and Z. That gives you a vector which is what? Orthogonal to the plane of incidence. Or no, yeah, no. Orthogonal to the RZ plane. All right? Then, the other one, we just cross X1 with Ri. That gives you a vector orthogonal to that vector. Okay, go through the code, you'll see.
So the Ri, so you define different the Z component from the X and Y.
Yeah, you need, because the global coordinate system, we're talking about everything in this global coordinate system's origin here, but the feed had an origin there. So you have to kind of have to shift it back. Normally you would have a new coordinate system, a separate one for the feed, but that made it more complicated. You have to use Euler and angle transformations and all of this, so it's easier to do that, yeah? Okay, so, all right, now we compute the reflected field. The reflected field, since we know the incident pencil tangential vectors, we reflect them off the surface by using the formulas that we had in the notes to get the reflected tangential pencil coordinate vectors. Then we calculate the projection matrices now that we have the incident and the surface. Incident, surface, incident, surface, incident, surface, right? The PI matrix, the projection of all, the dot product between all the tangential vectors. Whoops. Remember, we had that here. Here is the projection matrix definition, right? Here it is right here. So X incident 1 dotted with X surface 1, X incident 1 dotted with X surface 2, and so forth, right? And we found that P incident equal to P reflected because we use this formula to find X reflected versus X incident. And you'll find both those formulas in the code, yeah? Right here. So here are those formulas for X reflected. And now that we have the incident and surface, we can calculate PI. And P33 here is nothing but the dot product of Z and N, all right? Okay, P33 incident, right? Now we can calculate Q reflected here using the formula that we derived for Q reflected right there, yeah? So that appears in the code right there. All right. Then we have the reflected Q matrix we call eigen again in MATLAB with the reflected Q matrix. And we can calculate XR1 and XR2, and then we can take the cross product to get the Z of the reflected pencil, right? Now what we have to do is take the incident field, calculate E reflected, take the incident field and calculate and apply the boundary condition for PEC with the reflection coefficient. And what I did here was you do negative N cross with E incident. That gives you the tangential components of E incident. You negate those. Then you add back the normal component by doing the dot product of N with E incident and multiplying that by the normal. So I just negated the tangential components only, yeah? All right, now we have to solve, so we've calculated the reflected ray, right? So now we're here at this point, and we know this, we know the reflected coordinate pencil, right? The reflected pencil's coordinate vectors. And we know the reflected field at this point of reflection. Now we know the reflected Q matrix. Now we just have to propagate it to the aperture. But we need to solve for the intersection point of this reflected ray with this aperture parameterization. For you guys, you're going to change this sphere into a paraboloid, right? And this surface into a hyperboloid. All right. So we have to do another ray intersection solution, right? So here we have the intersection point. First, the intersection point of the surface. We just evaluate our incident ray coordinate or incident ray parameterization at the t that we solve for. This is the intersection point, position vector from the global origin to the intersection point on the sphere. All right, that's our B. We need that because a ray is parameterized as, so here's a position vector R, a t of a ray of a straight line. It starts with B, and then there's a tangential vector A that we need, right? B is this point here is the point on the sphere of intersection. So that's the initial point on the ray that we need. And then we parameterize the ray as X ray aperture. That's what AP means. So you have the initial point as the X coordinate. Then we have T dotted with X multiplied by Z, dot of Z hat, or X with the Z reflect. Okay, so let me show you. So here's a sphere. Here's a position vector R. We call this one the intersection point in the code. And then we have this point. We want to go to this point now. So the parameterization of a point on this ray, RAP, for example, is R plus T times a tangent vector here. But this unit vector, which is the tangent to the ray, is the Z of the reflected pencil coordinates, right? The axial ray's tangent vector is the tangent vector to the reflected ray. So all we have to do is dot that Z with X, Y, and Z to get the tangent vector, right? I realize it's probably hard to see it from where you guys are, but go through the code, okay? Now here's the parameterization of the aperture plane, which is a sphere again, but you guys want to change that paraboloid. All right? Okay. Now we do the same thing. We solve. So we have three new variables, t, u, and v, but for the aperture. And we set those three parameterizations equal, the x and the y and the z. We have three parameters to solve for t, u, and v. We have three equations, the x component equal to the x component of the surface, the x component of the ray equal to the, or the y component of the ray equal to the y component of the surface, z component of the ray equal to z component of the surface. So that system of three equations with these three unknown parameters allows you to solve it. All right, and we do the same thing. If it comes out empty, the ray didn't intersect the aperture. If it does, then we convert it into double data types. All right, we're almost done. Now, we compute the aperture field. So the position vector, now that we've solved for TAP and VAP and UAP, which are the parameters, we know the intersection point. We evaluate the ray's parameterization at that TAP, and that gives us a parameterization of the ray, which goes from to this point. Here's this the aperture, right? This R here is what we call intersection point AP now, which is this. We just evaluate our parameterization at the T that we solve for. That gives the intersection point with respect to the parameterization of that ray. All right, now, the length, what am I doing here? LAP, which is the length, is the vector norm. Oh yeah, so the length of that vector, you just find, you find the norm of that vector, the 2 norm, you get the length of that vector, so that gives you the length to there. All right, but why? That's incorrect. Oh no, that's good. Sorry. Yeah, so here's this, and this, right? I don't know what I use this for, as a matter of fact, the LAP. I don't think I use it. But here, the S is what matters. That's the norm of, so here's this, right? Here's the sphere, here's the aperture plane, here's a point, which we call intersection point. Here's another vector, position vector, which you call intersection point AP. The norm of the subtraction of those two is the 2 norm of that, x1 minus x2 whole squared, square root of x1 minus x2 whole squared, plus y1 minus y2 whole squared, plus z1 minus z2 whole squared, gives you the length of this ray, right? And that is our S. Okay. Now we propagate the Q matrix from the reflection point, Q reflected, to the Q aperture, which means we use the formula where it's the inverse of the Q matrix plus S multiplied by the identity matrix. I don't know if you guys remember that formula. Let me go find that for you. How to propagate a Q matrix. Is it, it's here. I think it's around here somewhere. Is it this one? No. Oh, here it is. This is how you propagate a Q matrix. All right. Okay. So Z times the identity plus the inverse of the Q incident or Q reflected is equal to inverse of Q at the aperture plane. All right. So let's go there. Here. So that formula is here. Now that we have the Q matrix at the aperture plane, we can calculate the divergence factor by using this formula. Let me show you that. The divergence factor is given by, it's that formula. Yeah, this is this formula. The square root of dA at sigma naught over dA at sigma, but we know that dA at sigma naught over dA of sigma is equal to the ratio of the determinants. So the square root of the ratio of the determinants of the Q matrices at 2 different points gives you the divergence factor. All right, so let's go back here. So that's exactly what we do in that line of code right there. Now we can calculate E at the aperture. E reflected multiplied by the divergence factor multiplied by E to the minus JKS, where X is the norm of the ray which goes from the intersection point of the sphere to the intersection point of the aperture. Yeah? All right. Now I calculate the magnetic current density in the aperture plane as minus 2 n crossed with E. Why is it minus 2? I use the surface equivalence theorem here by saying that first I find J equivalent and M equivalent on that surface, but then I don't care about the field inside of the aperture sphere, so I fill it with PEC, rather, sorry. I fill it with PEC and I short out the J. But now I have only M left, but that M is in the presence of PEC. To get rid of the PEC, I use image theory, get rid of the PEC and double the magnetic current, all right? So I calculate that in the aperture, and that's exactly what I calculate there. Then I store everything, all right? All right, then I plot the ray. Then I do some plotting of the aperture fields here, okay? I'm not gonna go through it because I spent too much time today on this. I need to get further, right? Okay, so go through the code. That's the last of the code. All I do here is plot the aperture fields. Yeah? Okay, good.
All these codes we consider both axial and paraxial rays.
Well, no, so yeah, in a sense, it's implicit though. You consider only the axial ray. I only have to trace the axial ray, right? I have to trace this ray, find its intersection point, and then trace its ray. But when I calculated the Q matrix associated with the reflected wavefront, I had to use the formula for a Q matrix of the reflected wavefront, which was derived by considering the paraxial rays and the surface and the incident Q matrix, right? So it's implicit. That's why when I was going through that long derivation, I was saying, you know, there's a lot of derivation here, but at the end, we just need this result, right? So you don't have to consider all these coordinate systems in the paraxial coordinate systems in the wavefront, incident pencil. You don't need to do all that. You just need the Q matrix formula, but it was derived by taking into consideration a pencil of rays and all of that with the paraxial rays, right? Okay, good. So you guys, once you use this code and do your homework problem, that's a significant achievement as well. Your 3D method of moment problem is a super, super good achievement. And this is also a super cool achievement. You know, you're calculating the geometrical scattering. This is how people used to do it. They used to launch rays at the subreflectors, trace them to the main reflector, calculate physical optics current, and integrate that to go to the far field. But now you have computational power, you can probably do the whole thing. But still, maybe not. If it's a big reflector, there's no way. So you got to do ray tracing, right? I mean, just this sphere example, remember, this took hours to run. It's a 10 lambda diameter sphere. And this took only a few seconds in MATLAB.
So I still didn't get how the field goes to the shadow region.
We don't calculate shadow, right? So the rays, remember, if you look at this, the rays are only going to intersect in the front here, right? They can't go to the shadow. If you look at this figure down here, what's happening here is you can't trace any rays beyond the shadow boundary. So if you were to calculate the far field from the currents in that aperture plane, then you would only have samples in the front half, right? And of course, a sphere has scatter fields behind it and all that. So it's for a sphere, it's probably not the best approach, but it works well for the reflectors, right? Paraboloids and hyperboloids. All right, so let me introduce this. We're supposed to get through here. So geometrical theory of diffraction, we're going to dig into that now. So what's the difference now? Our screen sigma has a sharp edge here now, right? This sharp edge has an incident pencil, but what happens when you have an incident pencil on a sharp edge, instead of getting one reflected ray like you would expect with the angle of incident equal to angle of reflection for like a flat surface or even a curved surface we saw, right? The curved surface still has Snell's law of reflection. If it's a sharp edge, you actually get a whole family of rays with that same angle, right? So this incident has beta, and with respect to the tangent to the ray, a whole cone of angles called a Keller cone with the same angle beta. It's kind of like this. If you have a surface and you have a point incident and the reflected field is the same angle, theta incident equal to theta reflected, then that's with respect to the plane of incidence. So there's some tangent, let's say, and a normal. Theta incident's in that plane that has tangent and normal. Theta reflected is also in that plane. So theta incident equal to theta reflected. But if I have a sharp edge now, and I come in like this, then there's a whole infinite number of normals. They spin all the way around the tangent, right? So you can imagine that I have a tangent vector still and a normal vector, and theta incident is still theta reflected, but there's a whole 360 degrees of the normal vector, right? So that's valid for all tangent and normal vectors to a sharp edge, which you can think of as having. So that means the reflected ray now becomes a cone. That cone allows you to penetrate into the shadow zone. It's called a Keller cone diffraction cone. You're going to read Keller's paper. So consider a typical diffraction point or a diffraction problem with a perfectly conducting screen, but now has an edge. We call the edge gamma. This is a sharp edge, gamma. All right? A zero wedge angle being illuminated by an incident field. All right? The asymptotic solution of the total field is what we want to determine. The geometrical optics field we already learned has E incident plus E reflected, right? Failed to predict a shadow field in the shadow zone and therefore fails to account for the diffraction phenomena. Means that, let's say the incident field's coming here, right? Then normally there'd be a shadow boundary here and there'd be nothing behind this screen. Imagine the screen's like this, a sharp corner maybe even, and the incident field's coming this way. So the shadow boundary's like that, right? And if the corner's like that, then you get nothing back here in this area. But if now you have this coming in, a Keller cone is created, and some of those rays go into the shadow zone. All right? Okay. To account for diffraction, we will introduce Keller's theory of diffraction. In short, this theory adds an additional component to E total. That additional component now is called E diffracted. So we have EGO plus E diffracted now. All right? And EGO has E incident plus E reflected. All right? So E diffracted is also given by E diffracted incident plus E diffracted reflected. So the incident field could have a diffraction, and the reflected field can also diffract, right? And we'll understand that. Now, look at this, k to the minus 1/2 in the Lunenburg-Klein expansion for the diffracted field, right? We expect that. So there's a diffracted phase function, and there's a diffracted amplitude, and it's still an expansion in terms of inverse power of k, but now they're half integer order, k to the minus 1/2. Okay? And then there's also the there's a plus sign missing here, sorry. Plus sign goes there. No, sorry, the plus sign is there, it's here. It's correct the way it's written. All right. So some preliminary remarks can be made about the diffracted field. The diffracted field, E diffracted, is of order k to the minus 1/2. And it's asymptotically smaller than the geometrical optics, which is of the order k to the 0. Right? In general, E diffracted is non-zero everywhere. There's no shadow boundaries, no shadow region of the diffracted field. Just as EGO consists of two symmetrical parts, incident and reflected, the diffracted field also contains two symmetrical parts, E diffracted incident and E diffracted reflected. E diffracted incident is associated with the incident field, and E diffracted reflected associated with the reflected field. These two parts have the same phase, but different amplitudes. We'll understand that. Since E diffracted is an asymptotic solution to Maxwell's equations, it should also satisfy Maxwell's equations, obviously. Okay, let's see the law of edge diffraction. The surface S diffracted equals to a constant. Remember, this is a phase function for the diffracted field. It equal to a constant defines a diffracted field wavefront, which is orthogonal to the diffracted rays. Here's a diffracted ray. There's a wavefront orthogonal to it. Here's a diffracted ray, a diffracted wavefront orthogonal to it. All diffracted rays emanate from the edge gamma of the screen sigma. They all emanate from the edge at this point. If we consider a neighboring point, let's say here, then this has its own diffracted ray cone, right? And all points along this edge are going to have diffracted Keller cones, all right? Consider an incident ray in the direction sigma incident, right? Here's sigma hat incident. Oh, shoot. Which meets the edge gamma at some point O, which is the point of diffraction, and makes an angle beta incident. So here's beta incident with the tangent T to the edge at the point O. it makes an angle beta with that tangent, right? Such a ray gives rise to a family of diffracted rays which emanate from O and make the same angle beta with T. So all rays with this beta angle with respect to, so beta is the angle that the incident field makes with the tangent, and beta is the same angle, just like the law of reflection, Snell's law, but now it's the law of diffraction because it applies to an entire cone with that same cone angle. In other words, the edge at each edge point R illuminated by E incident generates a cone of diffracted rays with the cone semi-angle beta and vertex at the edge point here and its axis as the tangent to the surface or tangent to the edge. The fact that beta equal to beta incident, so beta is the diffracted cone angle and beta incident is the incident field's angle with respect to the tangent to the edge, is known as the law of edge diffraction, which is the counterpart for Snell's law of reflection. Okay? All right, that's as far as we can get today. But we still have 3 lectures after this left in this course, right? Holy moly. We'll get through GTD for sure. All right, start your homework as soon as you can. And we'll probably even get to UAT and UTD. And we were going to talk about Green's functions a little at the end. So we'll do all that still, all right? But start your homework and try to take that code and do something with it, yeah? And any questions?